Hello everyone, and welcome to this video which demonstrates a modern application security architecture using F5 Distributed Cloud Web Application and API Protection, or F5 WAAP. This architecture is designed to help our customers more easily and quickly deploy secure applications via a common set of application security capabilities. I'm Kevin Delgadillo, Principal Product Manager at F5, and I'll be providing a high-level introduction to the solution, what it is, what problems it solves, the value that it brings, and the basics of what it does. Daniel Stokes and Michael Kennedy are technical solution architects here at F5 who put this solution together. They've created some demo videos with more technical details, which we'll walk through a bit later. Adaptive applications utilize an architectural approach that facilitates rapid and often fully automated responses to changing conditions. For example, new cyber attacks, updates to security posture, application performance degradations, or conditions across one or more infrastructure environments. Unlike the current state of many apps today that are labor-intensive to secure, deploy, and manage, adaptive apps are enabled by the collection and analysis of live application performance and security telemetry, security management policies, and advanced analytic techniques such as machine learning and automation toolchains. Two key components of F5's Adaptive Apps vision are to help our customers speed deployments of new apps and more rapidly detect and neutralize application security threats. In today's digital landscape, the need for modern, simple, consistent, and scalable application security has become increasingly critical. Simplicity is crucial to ensure that security measures are practical, easy to understand, quick to deploy, and easy to maintain. In other words, simplicity is crucial for accelerating secure application deployments. Consistency ensures that security standards and best practices are uniformly applied across all applications, reducing the potential for gaps or vulnerabilities and speeding up secure application deployments. Modern application security practices must address growing challenges by adopting scalable solutions that can accommodate the increasing demands of diverse and dynamic applications. This F5 Adaptive Applications Demo Kit shows a simple and easy-to-deploy application security solution that delivers scalable, consistent, and comprehensive app protection, thus enabling accelerated secure application deployments. We show how you can use F5 Distributed Cloud WAAP to enable differentiated and tiered application security capabilities as appropriate for your low-risk, medium-risk, and high-risk applications. Specifically, this demo kit demonstrates the following: deploying the F5 Distributed Cloud WAAP in both Regional Edge (RE) and Customer Edge (CE) within a customer's traditional on-prem data centers to provide tiered application security for external and partner traffic respectively, and deploying NGINX Plus with third-party open source tools to enable malware analysis and defense for all application traffic. As previously stated, this solution is designed to help our customers more easily and quickly deploy secure applications via a common set of application security capabilities. Our customers find it difficult, time-consuming, and costly to ensure their mission-critical workloads are protected from real-time threats while providing consistent access control, visibility, and analytics across their deployments in an automated fashion. Here we demonstrate how customers can use this modern security architecture to more easily and quickly deploy secure applications, make better informed remediation decisions regarding their security posture, and protect against potential threats in an automated fashion. With this modern architecture, our customers can enjoy the following benefits: consistent, easy-to-deploy WAAP security solution for all app deployments managed by F5 XC, accelerated secure application deployments, multi-tier security architecture providing differentiated levels of application security to optimize SecOps efficiencies, and horizontal scaling using a CE fleet across application deployment environments. At the heart of this solution architecture is the tiered F5 XC WAAP capability shown here. Deployed within the F5 Distributed Cloud Regional Edge and Customer Edge, it provides 3 tiers of application security for low-risk, medium-risk, and high-risk applications. All of these components are collapsed into a single red tiered F5 XC WAAP icon on the left to make it easier to show how and where it is deployed in the regional edge and customer edge on the slides that follow. First, we show where it is deployed in the F5 XC Customer Edge, or CE. Here, the tiered F5 XC WAAP is deployed on the F5 XC CE node, where it provides application security protection for all partner and B2B source traffic. Also shown is Nginx Plus with some third-party open source tools which provide malware defense for all traffic. While Nginx Plus can integrate with any standard ICAP service, we will use ClamAV with a Squid ICAP server for simplicity. These are chosen for illustrative purposes only, and we make no explicit endorsement nor recommendations for these particular tools. Here, applications are deployed in the data center behind BIG-IP, which provides traditional application services including local traffic management, or LTM. With this security architecture, existing BIG-IP Advanced WAF, or AWAF, customers have the flexibility to continue using AWAF here and/or migrate their AWAF application security capabilities to F5 XC WAAP using the F5 Policy Supervisor. Here we bring it all together and show where the tiered F5 XC WAAP is deployed in both the F5 XC RE and CEs. This represents the overall solution architecture for this demo kit. The product scope of this demo is comprised of the following F5 components: F5 Distributed Cloud, F5 Distributed Cloud WAAP, F5 Nginx Plus, and F5 BIG-IP. Deploying F5 XC WAAP in the regional edge provides tiered application security for externally sourced traffic. Deploying F5 XC WAAP in the customer edges provides tiered application security for partner and B2B source traffic. Deploying Nginx Plus with third-party open source antivirus and malware analysis tools in the CEs provides protection for all traffic, both external and partner sourced. This architecture utilizes one F5 XC customer edge node per data center. Note application deployments are not limited to traditional on-prem data center environments as shown in this simplified example. Applications deployed within F5 XC REs and CEs, whether on-prem or in public cloud, can also enjoy the same F5 XC WAAP-enabled tiered application security benefits. This modern architecture enables you to more easily deploy a common set of application security capabilities using F5 XC as a single consistent deployment console. Additionally, given application security does not fit a one-size-fits-all model, we show how to enable tiered application security capabilities as appropriate for your low-risk, medium-risk, and high-risk applications. Specifically, we demonstrate the following: enabling the F5 XC global network, deploying F5 XC WAAP in F5 XC regional edges to provide tiered application security for external application traffic, deploying F5 XC WAAP in F5 XC customer edges within traditional customer on-prem data centers to provide tiered application security for partner and B2B application traffic, deploying F5 XC HTTP load balancing in REs to distribute traffic across multiple CEs and customer data centers to maximize application availability and resiliency, deploying traditional applications behind BIG-IP in on-prem data centers, and deploying Nginx with ClamAV and a Squid ICAP server in F5 XC CEs to enable malware analysis and protection for all application traffic. Now let's look at the demos.
Let's talk about how to connect an F5 BIG-IP to F5 Distributed Cloud as an AppStack site. Up on the screen, I have the dashboard for the AppStack site created with the Terraform files we will explore in this video. Before we look at the Terraform files, there is one resource we need to make sure exists before we get started, and that is a site token. Site tokens can be found under the Site Management menu. For the automation to work, we will need at least one site token in the tenant. The name of the token does not matter. We have several here, so we are good to go. If you do not have one, click on the Add Site Token button to create one. Now let's look at the Terraform files we used to make this happen. Our goal is to set up a distributed cloud node and have it register with Distributed Cloud. For this demo kit, we are going to create the Distributed Cloud node in VMware vSphere. This means we will need two Terraform providers, Volterra for the distributed cloud management, and vSphere to create the distributed cloud node as a virtual machine. Now let's go to the top of the main Terraform file. Here we have the token resource. This resource represents the site token we made sure existed in the beginning of this video. And it is a bit odd. It is better to think of this as a data source instead of a resource, since it will contain the information of the first site token on the distributed cloud tenant and does not actually manage the lifecycle of any distributed cloud resource. We will make use of this later to retrieve a token UUID for the distributed cloud node. Next, we have the creation of the AppStack site. Here we use some variables to maintain consistency between values across resources. Inconsistencies in the site name, host name, or certified hardware string will cause the automation to fail. You can review the variable definitions, which are in their own file, for more information on these variables. After the distributed cloud node boots, it will attempt to register itself with distributed cloud. We use these next two resources to accept that registration and to avoid needing to do it in the GUI. We have a sleep here to make sure the distributed cloud node is running and attempting to register before we go looking for that registration. Again, you will see some variables here to ensure consistency in values. Once the distributed cloud node completes registration and the site is working, we can route traffic to the big IP as an origin server and an origin pool. The settings here will depend on your network configuration and load balancing needs. That covers the distributed cloud resources, so let's look at the vSphere resources. What we have here is a basic example from the vSphere provider documentation with some modifications. As you can see here, we are deploying an OVA file provided by Distributed Cloud. You can find a link to all available images in the demo kit repository. You will find plenty of WAAP properties to configure the distributed cloud node to your needs. Here we'll look at some required properties. The host name, certified hardware string, and site name we have already seen as part of configuring distributed cloud resources earlier in this video. And here we are fetching the UUID of the site token that the node will need for registration. Other than that, we need to set latitude and longitude values and change the default admin password. And there you have it, the basic building blocks to get a big IP connected to distributed cloud. For more details and full demo kit, please check out the Adaptive Applications GitHub repository. Let's talk about how to automate the creation of a tiered security architecture in F5 Distributed Cloud using Terraform. We will set up distributed cloud HTTP load balancers and application firewalls to secure traffic that we will be sending to a single origin pool. That pool is the same one we set up in the previous segment, and it distributes traffic to our data center servers using host-based routing. So, why bother setting up more than one load balancer and firewall if we send all the traffic to the same origin pool? The answer is to prioritize security resources where they are most needed. For our low security risk applications, we can apply security features that do not require application-specific tuning and are less likely to produce false positives that require further investigation. For our high security risk applications, such as something involving personally identifiable information, we can spend more time tuning the security based on application details and spend more time dealing with potential false positives. Now, let's look at the Terraform files. For this configuration, we only need the Volterra provider in order to configure distributed cloud resources. Since the security settings you will use will strongly depend on your security needs and applications, we'll mostly focus on just one tier. After that, I will give you some tips on how to find the settings appropriate for your needs. Now, what is going on at the top of this load balancer resource? A load balancer is limited to 32 domains. If you want more than 32 applications in a single security tier, you will need to create multiple load balancers to work around this limitation. This Terraform code applies that workaround automatically, which means you just need to specify all the application domains in the appropriate variable, and you're good to go. Now, the rest of this is simpler. We are setting the load balancer to accept HTTPS traffic and send it to our origin pool. And then we have some security settings change from their default values, including attaching an application firewall configuration, which you can see up here. If we take a quick look at the other tiers, you will see that they follow the same pattern with different security settings. Since these security settings will depend on your needs, let me leave you with some tips on writing the appropriate Terraform code. First, you can find information about these settings in the Volterra provider documentation under the Volterra HTTP load balancer and Volterra app firewall resources. Another option is to use the GUI to guide your configuration. After you have configured an object, you can view its JSON description under the Git spec property. The property names and values used here, the same ones used by the Terraform provider. You can reference the provider documentation to work out any Terraform specific details. For more details and the full demo kit, please check out the Adaptive Applications GitHub repository.
G'day. Welcome to this deployment video of a malware and antivirus protection as a service with F5 Distributed Cloud. Here is deployment we'll be focusing on within this video, specifically what is deployed within the DMZ, the Nginx and malware component. For that, we'll be using ClamAV. We step over to the Adaptive Apps repo. We will be stepping through the README, which lists all the install instructions and configuration variables that are used for this deployment solution. Now we'll just do a quick git clone of that repo to the local system. Now this will deploy to AWS using Terraform, and as you can see with all of the Terraform files here. And we'll deploy a F5 Distributed Cloud CE appliance in a as a Vault stack combo, which will allow us to extend manage Kubernetes across to this appliance. For this, we will need environment variables, which I've failed to enter correctly. The joys of regex on command line. So just quickly update this. Done. And now we can see here the var file we'll be using for this Terraform deployment. As you can imagine, this is all programmatic ecosystem. So now we will perform a Terraform init, which will download the required modules along with the AWS and Volterra provider that will be used for this infrastructure as code. So with the CE deployed within AWS, we can then use standard Kubernetes or kube control commands and APIs to allow us to deploy within to the managed Kubernetes secure environment of F5 Distributed Cloud. Now we're just installing the providers here. Now we shall do a plan to validate everything is correct, using both the AWS secrets, which are required for the EC2 instance of the Vault Stack combo that is deployed, along with others. Now we shall apply this with an auto approve flag, and that will spin up the required infrastructure, being the VPC, the EC2 instances for the Vault Stack combo that will serve the managed Kubernetes component, and we shall step back to this shortly.
A few moments later.
Now that we're back, we'll do a Terraform state list, which will show us all the components that have been deployed. As you can see, all the EKS components, jump host, along with the VPC. Now if we step over to Distributed Cloud Console, we'll be able to see the CE that has automatically registered as part of the Terraform deployment. This can be found in the Multi-Cloud Connect. If we check outstanding pending registrations, if we step over to other registrations, here we can see the F5 XC ICAP. Now if we check over to the VPS sites, we can see also the corresponding information here. Pull up the metrics. System is 100% reachable. All the system metrics are green. We have complete data plane connectivity. There is nothing deployed within this managed Kubernetes CE. Stepping over to distributed apps to verify. If we choose the right namespace, here we can see the F5XC managed Kubernetes, or with running pods. The node, for brevity of this demo, we are only using one instance. No deployments apart from the system deployments. Do a quick search for ClamAV, nothing has come up. Now if we go back to the managed Kubernetes and download the configuration that we'll be using as part of the kube control or the Kubernetes API functionality. So using this, we'll just copy that across. Now to get all the pods, using that kube config, cut and paste. Oh, that's not going to work. There's nothing deployed, so there's nothing in default. So we'll do all namespaces, and that will give us the namespace for kube system and the VES system, along with the monitoring, which is all the components currently running on the CE. We'll now deploy the ClamAV REST API interface, which is the Nginx and a Node.js app that communicates back to the ClamAV daemon. We'll now deploy the daemon, followed by the daemon service. Get the deployments to validate that it has deployed successfully. If I can get deployments, we'll pass the kube config. Pass. I'll get this right in a second. Cut and paste, I still fail. Here we can see that we have the CRA and the ClamAVD stepping back over to Distributed Cloud Console. And if we have a look within the cluster itself, we have now 35 pods. Previously we had 33. Now if we go where we had our previous filter, we can see there is the ClamAV daemon deployment, which is the pods that the REST API will communicate to, which is there as a CRA deployment. Now, because this is an internal service, what we will do is we will grab the port, the container port here. You can see the name being the REST API and the port that is required being 3000, and we will execute a kube proxy to allow us to validate that ClamAV has been successfully deployed as part of this demo. Cut and paste fail again. Let's get the pods. Let's get the pods. Here we're using I'm using, for brevity, the kube control aliases. Here we can see the deployments and the pod. So I'll just grab that, correct this command, which will then allow us to port forward to the correct pod. Go and go. There we have it. Now if we step over to another terminal window, just make that a little bit easy to read. Cut and paste again. And we'll make it a little bit, we can see that's come back as true, but we'll make it a little bit prettier using JQ. And there we can see the response for the REST API and the daemon itself. Thank you very much for your time, and thank you for all F5 engineers and Nginx engineers who assisted this.
Thank you for watching this demo video. Please be sure to reference the GitHub repository for documentation and additional details.